Hi everyone. Previously, we have introduced the multiplicative inverse of an integer a modulo a positive natural number n. In this section, we will continue our discussion and develop some nice properties when the modular n is a prime number. From there, as a nice application, we will prove the famous Wilson's theorem as a preparation for our upcoming study of the Feynman-Little theorem. To start with, recall that we have already seen when p is a prime number, any integer a that is not divisible by p has a multiplicative inverse modulo p. Moreover, this inverse is unique up to congruence modulo p. Actually, when p is a prime, we can go slightly further to see the structures of multiplicative inverses modulo p. To start with, let us prove the following proposition. Let p be a prime number. Then, for any integer a squared is congruent to 1 modulo p if and only if a is congruent to either 1 or -1 modulo p. The if part is really straightforward. Indeed, if a is congruent to either 1 or -1 modulo p, we can simply take square on both hand side, which implies directly that a squared is congruent to 1 modulo p. To justify the only if part, let us assume that a squared is congruent to 1 modulo p. From there, by definition of the congruence modulo, we see that p divides a squared minus 1, which is equal to the product of a minus 1 and a plus 1. Now, recall that p is a prime number, thus the Euclid lemma works and implies that either p divides a minus 1, in which case a is congruent to 1 modulo p, or p divides a plus 1, in which case a is congruent to -1 modulo p. This finishes the proof. Now recall that if we consider all equivalence classes achieved by congruence modulo p, there will be precisely p distinct classes represented by 0, 1, 2, 3 until p minus 1 respectively. Now given an integer a, what can we say for its multiplicative inverse based on the equivalence class of a modulo p? Well, there are a couple of possibilities. If a belongs to the equivalence class represented by 0, that is, if p divides a, then the inverse of a does not even exist. On the other hand, if a belongs to an equivalence class other than that of 0, then we know its multiplicative inverse must exist. And from there are still two possibilities. Either a belongs to the equivalence class of 1 or p minus 1. Notice that p minus 1 is congruent to -1 modulo p. Thus, in these two cases, the multiplicative inverse of a will fall into the same equivalence class as that of a. Otherwise, if a does not belong to the equivalence class of 1 or p minus 1, then a and the inverse of a belong to distinct equivalence classes. We remind the audience that our discussion here relies strongly on the primality of p. If p is no longer prime, then the consequences here might no longer be true. As an example, let us consider the case where p is equal to 7, and let us discuss the multiplicative inverse of a as a goes through 0, 1, 2, 3, 4, 5, 6. First of all, when a is equal to 0, since 7 divides 0, 0 does not have a multiplicative inverse. Now, for each of these 6 remaining integers, due to their co-primality with 7, we know that an inverse exists. Moreover, we can find some integer between 1 and 6 to serve as this inverse. If a is equal to 1, then the inverse of a is also equal to 1. Similarly, if a is equal to 6, then the inverse of a is also equal to 6 itself. Apart from these two integers, we see that the product of 2 and 4 is equal to 8, which is congruent to 1 modulo 7. Thus, 2 and 4 form a pair of multiplicative inverse with each other modulo 7. On the other hand, the product of 3 and 5 is equal to 15, which is also congruent to 1 modulo 7. In other words, 3 and 5 also form a pair of multiplicative inverses with each other modulo 7. You can see how this simple example has illustrated our previous discussion. With all these preparations, now we are ready to state the Wilson theorem. It claims that for any prime number p minus 1 factorial is congruent to -1 modulo p. To get some feeling, let us first verify this theorem by looking at p equal to 7. In this case, p minus 1 factorial becomes 7 minus 1 factorial, which is equal to 1 times 2 times 3 times 4 times 5 times 6, that is 720. This number is equal to 7 times 103 plus -1, which is indeed congruent to -1 modulo 7. Great! This has increased our confidence on the validity of this theorem, of course. Yet, to gain some inspiration for its proof, let us study more carefully which structure in this factorial ensures its congruence to -1 modulo 7. Actually, recall that in the previous example, we have checked the multiplicative inverse modulo 7 for each of these 6 numbers in the product. There we have already seen that the multiplicative inverse of 1 is 1, the multiplicative inverse of 6 is 6. Now if we forget 1 and 6 and focus on the 4 numbers in the middle, that is 2, 3, 4, 5, we notice that 2 and 4 form a pair of multiplicative inverses whose product is congruent to 1 modulo 7. Similarly, 3 and 5 form another pair of multiplicative inverses whose product is again congruent to 1 modulo 7. Thus, after pairing the 4 numbers in the middle into multiplicative inverses of each other, the product in the factorial becomes 1 multiplying another 2 ones, then multiplying 6, which is in turn congruent to -1 modulo 7. Now we see clearly how to prove the Wilson theorem in general. Actually, when p is equal to 2, the theorem states 1 is congruent to -1 modulo 2, which is true trivially. Yet, when p is greater than 2, due to its primality, it must be an odd number. And now we can deal with this factorial pretty much in the same way as we eat a shrimp. That is, we take off the head, we take off the tail, and we cook the part in the middle. More precisely speaking, since p is a prime number, each number in the product of this factorial has a multiplicative inverse, which can also be found in the same set of numbers. Now, the multiplicative inverse of 1 is 1 itself. The multiplicative inverse of p minus 1 is p minus 1 itself. If we take out these 2 numbers, the p minus 3 numbers in the middle, after regrouping, will form p minus 3 over 2 pairs of multiplicative inverses. Thus, the factorial is congruent to 1, multiplying another p minus 3 over 2 copies of 1s, multiplying p minus 1, which is just p minus 1, and is in turn congruent to -1 modulo p. As a consequence, we have proved the Wilson theorem.